Hey there, students. In this clip, we're going to be going over some examples on how to use the sandwich theorem to find limits. So before we start, let's go ahead and take a look at the formulas that we're going to be using to simplify the whole limit determination process. Okay, so write it down, formulas. All right, so the formulas I'm going to show you, I'm not going to be going over the detailed derivation of them. There's a video installment in this sandwich theorem playlist that goes over how to derive this theorem, this formula I'm showing you. Okay, this installment mainly goes over how to use this formula. All right, so the first formula is that the limit as x approaches 0 of sine x over x is equal to 1. Okay? In using this foundational formula, we can also extend it to more situations. Okay? So formula 2, the limit as x approaches 0 of sine ax over ax can be reduced into a over a, which equals 1. Okay, so you can see how Formula 1 is a special case of Formula 2. In the case of Formula 1, a is equal to 1. All right? Okay, number 3. The limit as x approaches 0, this is another formula you should master, of sine ax over bx is equal to a over b, just like this. In this case, the a and these two are the same. In this case, you're different, so you can reduce it. Okay? All right, number 4. The limit as x approaches 0 of sine ax over sine bx, this is equal to a over b, similar to that one right there. Okay? All right, now there are two other sandwich theorem formulas that you need to know. So number 5, the limit as x approaches 0 of x to the m sine 1 over x to the n, that's equal to 0. Okay, and number 6 is similar to that, limit as x approaches 0 of x to the m cosine 1 over x to the n. This one is also equal to 0. Okay, so note for 5 and 6, n and m have to be greater than 0. Okay? All right, so there you have it. So these are the formulas that you should memorize in order to be able to determine limits involving sandwich theorems really quickly without any complications. Okay? All right, so let's apply these formulas to some examples. So the task is to determine the following limits. Determine the following limits. All right, problem number 1. What if we want to find the limit as x approaches 0 of sine 5x over x? Okay, you see how this form is consistent with formula number 3. In this case, a is 5 and b is 1. So the answer is simply going to be a over b, or is just 5 over 1, which is just 5. All right, so there you have it. All right, let's take a look at question number 2. What is the limit as x approaches 0 of 4x over sine 2x? Now, this looks very similar to this case, but it's kind of reciprocated. All right, so how do we do this? Well, we just reciprocate this, and then we're going to take the limit of we'll reciprocate the value of the limit that we get after evaluating what's on the inside. Okay, so there are two ways we can do this. I'm going to use the reciprocal approach for this problem. So what I'm going to do is write this limit as x approaches 0 of sine 2x over 4x. So what did I just do? I reciprocated this expression, so let's put that, raise that to the -1. Okay? So now we're going to take the limit of this expression inside the reciprocal symbol. So this is going to become the limit as x approaches 0 of 4x, of sine 2x over 4x raised to the -1 power. Okay? So what is this limit in here? This limit is just like the a over b situation, ax over bx. So this is simply going to become 2 over 4 raised to the -1. 2 over 4 reduces to 1/2. And the reciprocal of 1/2 is 2. So there goes your limit. Okay? So this is one way of doing it, just reciprocating this expression and then taking the limit of that and reciprocating a result. Another way you can do this is you multiply the numerator and the denominator by 1 over 4x. The numerator becomes 1, and this denominator becomes sine 2x over 4x. And then you then have 1 over 2 over 4, and then when you simplify, you have 1 over 1/2, reciprocate, your answer will become 2. Okay? So that's another way of doing it. All right, let's go to question number 3. So how about if you want to find the limit as x approaches 0 of x to the third cosine 1 over x squared. Or if you wanted to find this limit. Write this again. 1 over x squared. All right, so if you take a look at this form, it's consistent with formula number 6, this one right here. So what do you think this limit is? It's simply 0. Okay, so let me show you why this is the case. Okay, using the sandwich theorem. You don't have to do this. I just want to show you why this is 0. Okay, all right, so we're going to call this the explanation of number 3, explanation of 3. This is just FYI. If you're curious, this will help satisfy your curiosity, address your curiosity. So explanation of number 3. Okay? So if you take a look at number 3, we want to focus on the cosine expression. We know that the cosine has a range of 1 and -1. Okay? The maximum output of cosine is 1, and the minimum is -1. So cosine is bounded between these two values. Okay? All right, so what if we multiply this entire expression by x to the third? What happens? So we're going to distribute this x to the third to all 3 terms. So our inequality becomes -x to the third is less than or equal to x to the third cosine 1 over x squared is less than or equal to x to the third. Okay? Now, what do we know about the limit of the boundaries as x approaches 0? Well, we know that the limit as x approaches 0 of the lower bound -x to the third is the same as the limit as x approaches 0 of x to the third. They're both 0 to the third, which is just 0. All right? So what does that tell me? It tells me that the limit of the middle expression is bounded between 0 and 0. Okay, so let's write that down. So 0 is less than or equal to the limit as x approaches 0 of x to the third cosine 1 over x squared, and that's also less than or equal to 0. All right, so by the sandwich theorem, what can we conclude? Since this expression, the limit as x approaches 0 of x to the third cosine 1 over x squared is sandwiched between 1 and 0, between 0 and 0 by the sandwich theorem, this value, this expression has to also be 0. Okay, so limit as x approaches 0 of 1 over x squared is equal to 0. All right, so this is just the explanation using the sandwich theorem. You don't have to do all this if it's not required. You can just use this formula to easily determine that the answer is 0. All right, so there you have it. All right, so for number 4, let's evaluate this limit. The limit as x approaches 0 of x to the third e to the sine 1 over x squared. So what is this limit going to be? You want to make a wild guess? Well, this is similar to the other case, to formula number 5, even though you have an e here. So this is going to be equal to 0. Okay? All right. Let me give you a brief explanation as to why that's the case using the sandwich theorem. Explanation of 4. So we know that sine x is between, the range of sine x is, sine is between -1 and 1. Okay, so we know that -1 is less than or equal to sine 1 over x squared, and that's also less than or equal to 1. All right, so how about we exponentiate all three sides of this equation using e as the base? So what if we go e, e, and then e? So e to the -1 is less than or equal to e to the sine of 1 over x squared, and that's less than or equal to e to the 1. All right, so we have this equation holding through because we exponentiated all three parts of the inequality with the same base. Now, what if we multiply the entire expression by x to the third? So multiply by x to the third. So that's going to yield x to the third times e to the -1 as less than or equal to x to the third e to the sine of 1 over x squared. And that's less than or equal to x to the third e. Okay? So what happens when we take the limit as x approaches 0 of the upper and the lower bound? What happens? The limit as x approaches 0 of x to the third e to the -1 is the same thing as the limit as x approaches 0 of x to the third times e to the 1. Because if you take this limit, it's just 0 times e to the 1 here. I mean 0 to the third times e here, which is 0, and then this is 0 to the third times e to the 1, which is also 0. So these two limits are 0. Okay? So what does that tell me? It tells us again that the limit of the central expression as x approaches 0 is bounded between 0 and 0. So 0 is less than or equal to the limit as x approaches 0 of x to the third e to the sine 1 over x squared, and that's also less than or equal to 0. All right? So by the sandwich theorem, what can we conclude? By the sandwich theorem, if a number is bounded between the same number, that number must be the value of that number, right? So by the sandwich theorem, we can conclude that the limit as x approaches 0 of x to the third e to the sine of 1 over x squared is also equal to 0. All right, so there you have it. Okay, let's go ahead and try another example. For number 6, what if we have the following limit? For number 6, let's write this down. Number 6, what if we want to consider the limit as x approaches 0 of sine x over 9x squared minus 6x. Okay? All right, let's take a look at this. If we plug in 0 directly, notice that we'll have an undefined expression. So can we apply the squeeze theorem here? Can we extract like a sine x over x, something of that nature here? Absolutely. Let's focus on the denominator first and simplify that. So this can be written as a limit as x approaches 0 of sine x over x. Oh, actually, we can take out 3x. That's a GCF there. 3x times 3x minus 2, like that. And then we can write this as the limit as x approaches 0 of sine x over 3x times 1 over 3x minus 2. And we can use the product property of limits to distribute the limit to these two terms right here. Okay, so we can see that this is going to be 1/3, and this is going to be -1/2, and this is going to be -1/6. That's the answer. But let me show you the work. Okay, so showing you all the baby steps. You have limit as x approaches 0 of sine x over 3x times the limit as x approaches 0 of 1 over 3x minus 2. Alright, so we're going to use the sandwich theorem here. In this case, a is 1, b is 3. So remember, we have ax over bx of sine is simply a over b. So this is going to be 1 over 3 times, this one we just plug in 0 into this expression. So it's 1 over 3 times 0 minus 2. So we have 1 over 3 times, this reduces into negative 1/2. And when we multiply it out, you get negative 1/6. Okay? So there goes your final answer. All right, let's try one last example. Then I'll give you some problems to try out to see if you've mastered this whole process. Question number 7. What if we want to find the limit as x approaches 0 of 1 minus cosine x over x squared? All right. We can clearly see that if we plug in 0 here, we're going to have a problem at the denominator. It's going to be over 0 and can't find out what the limit is. So what can we do here? How about we rationalize the numerator? Okay, let's rationalize the numerator. We're going to multiply by 1 plus cosine x and 1 plus cosine x. And your answer is going to become the limit as x approaches 0 of 1 minus cosine square x over x squared times 1 plus cosine x. Remember that if you distribute this, you do first, outer, inner, last, the middle terms cancel out, so you end up with this, okay? Now, using our trig identity, we recall that the identity, so trig identity, remember that sine square x, the Pythagorean identity, a variation of that, sine square x is equal to 1 minus cosine square x, right? So we're going to make use of that here to make a substitution in the numerator, okay? So let's do that. We're going to have the limit as x approaches 0. In the numerator, I'll have sine square x over x squared times 1 plus cosine x, okay? Let's break this down so that everyone can see, although it's obvious that this limit is going to be 1 over 2, but let me show you how the whole process is. Okay, so I'm going to break this down so it's easy to see that this limit is 1/2. So we're going to write this as a limit as x approaches 0 of sine x over x times sine x over x, because sine square x just means sine x times sine x, and then x squared, you know what that means, times 1 over 1 plus cosine x. So now we're just going to take the independent limits of this factored terms right here, this product of terms. So this is going to become the limit as x approaches 0 of the first term, which is sine x over x, times the limit as x approaches 0 of sine x over x, times the limit as x approaches 0 of 1 over 1 plus cosine x. Okay? So to simplify this, we're going to have this limit becomes 1 using the sandwich theorem, the first one I showed you. Second one becomes 1. And then the last one, you just plug in 0 there, it becomes 1 over 1 plus cosine 0. So all you have is 1 over 1 plus cosine 0 is 1. So yeah, your final answer is 1/2. Okay, so there you have it. All right, so how well did you understand these examples? So what I'd like to do, I'd like you to try these problems, and then post your answers in the comment section below so I can see if you've mastered the whole process. Or if you have any complications, you can just post what your confusions were in the comment section below, okay? So determine the following limits. This is your test to see if you've mastered the process. Determine the following limits. Number 1, find the limit as x approaches 0 of 4 sine 3x over 5x. Number 2, determine the limit as x approaches 0 of 3x squared sine 1 over x to the 4th. And then number 3, requires the use of identities. Find the limit as x approaches 0 of 5x cosecant 4x. Okay? And then question number 4. To demonstrate your understanding or mastery of this concept, find the limit as x approaches 0 of sine x over 2x minus 5x squared. Okay? So try out these problems and then post your answers to these problems in the comment section below so I can see if you mastered this whole process. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here, and also don't forget to post a comment about your answers or confusions, or even to let me know what you think about this presentation. More clips can be found on mathleticsub.com/calculus, or you can just scan this QR code for direct access. Thanks again for watching, and have a wonderful day.